Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into one of the deepest, most misunderstood mysteries in all of physics. The idea that energy, that sacred constant we were all taught to believe in, might not be truly conserved. What if the universe, in its endless unfolding, quietly bends that rule? What if time itself flows not because of clocks or motion, but because the universe keeps finding new ways to let its energy slip away, one grain of order at a time? But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe. Only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now feel free to dim the lights, maybe turn on a fan for a soft background hum, and let the edges of the day begin to blur. We're about to drift into one of the most beautiful paradoxes in all of physics, a truth that seems solid until you listen closely enough to hear it hum beneath everything. So, when your thoughts have settled and your breathing has found its quiet rhythm, let's gently begin our journey into the biggest misconception in physics, where the law of energy meets the mystery of time itself. And if your mind starts to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. Imagine yourself far from everything, out in the quiet black of space. You're an astronaut floating weightless, surrounded by stars that look so still they might be painted on glass. You raise your arm and with a calm motion you throw a small rock forward. There's no air, no wind, no friction, nothing to stop it. So, by Newton's law, it should keep drifting forever, gliding in a perfect straight line, never slowing down. But in the real universe, that isn't what happens. Over immense stretches of time, the rock begins to slow, almost imperceptibly. Eventually it comes to rest, not because of drag or gravity, but because the stage beneath it, the very fabric of space, is expanding. You might ask, where did the rock's energy go? There was no collision, no friction, no heat, and yet the energy that once carried it forward seems to fade into nothing. It's a simple, quiet mystery, one that puzzled even the greatest minds of the 20th century. At the dawn of modern physics, energy was a kind of faith. It was believed to be absolute, a cosmic currency that could never be lost or created, only traded from one form to another. From the spark of a match to the orbit of planets, everything obeyed that rule. The idea of energy conservation was the bedrock beneath every theory, every equation, every experiment. But as the century turned, the universe began to challenge that faith. When Albert Einstein crafted his new vision of gravity, the general theory of relativity, he realized something troubling. His equations could describe how space bends and time stretches, but they didn't clearly show where the energy of that bending actually lived. Was it in the fabric of space itself? Was it hidden inside the curvature, or the motion of stars, or the invisible tension of gravity? No one could say for sure. Einstein, always searching for harmony, believed that the universe must still keep its balance, that total energy had to be conserved, even if it took on strange new forms. But then a quiet mathematician named Emmy Noether appeared, and gently showed him that his beautiful belief might not hold. She proved something astonishing. The conservation of energy and every other conservation law isn't a divine truth, but a consequence of symmetry. Imagine for a moment you're standing in a perfectly still field. If you take a few steps to the left or to the right, the field looks the same. That sameness, that symmetry, is what gives us the law of momentum. If you turn around and spin, the world around you doesn't change. That symmetry creates angular momentum. And then there's time. If the rules of physics are the same today as they were yesterday, that time symmetry gives us conservation of energy. It's an elegant connection. Where there's symmetry, there's conservation. and where symmetry breaks, something changes forever. Noether's theorem, written in 1918, quietly reshaped the foundation of physics. It told us that energy is conserved only if time behaves like a perfect mirror, if every second that passes is just like the one before. But the universe, it turns out, doesn't keep perfect time. When we look at the night sky, we're not seeing a static picture, we're watching space itself stretch. Distant galaxies drift apart, light waves stretch with them, and time ripples unevenly through it all. The universe isn't symmetrical in time, not really. It's expanding, evolving, aging, and that means, in the grandest sense, energy may not be conserved. It's not that the rock's energy went anywhere, it's that the universe changed the meaning of motion itself. As the cosmic fabric stretched, the rock's movement slowed, not because it lost power, but because power itself became a different language. It's a humbling thought. We like to imagine the cosmos as a tidy machine, every gear turning in balance. But in truth, it's more like a breathing organism, inhaling space, exhaling time, constantly trading one kind of order for another. The old promise that energy cannot be created or destroyed was never a lie. It was just a local truth, one that works beautifully in the small calm patches of the universe we can touch. But beyond those patches, across billions of years and galaxies, that symmetry begins to fray. Time stretches unevenly, and what once was energy simply fades, like sound losing itself in a vast cathedral. And maybe, in that fading, lies the reason we have time at all. Because if the universe ever stopped changing, if energy stayed perfectly balanced, if symmetry were flawless, then time itself might have no reason to move. It's strange to think that everything we know, from a falling leaf to a heartbeat, might exist only because perfection is broken. Because somewhere, deep beneath the stars, the universe keeps forgetting just a little bit of its own energy. As we drift further into the story, this small crack in the law of energy will lead us towards something even deeper. The quiet engine that makes time flow, life emerge, and every star slowly cool. The hidden rhythm that hums beneath everything, entropy. Albert Einstein's world was not one of silent laboratories and glass flasks, but of thoughts that stretched like light itself. Ideas that began in small questions and grew until they touched the edge of everything. In 1915, he stood at the front of a lecture hall in Göttingen, Germany, his blackboard filled with curving symbols that even other physicists barely understood. He was building something magnificent, a new description of gravity, not as a force, but as a bending of space and time. Yet in the midst of this creative storm, a single question kept tugging at him like a loose thread. If space and time themselves can bend and stretch, then where does their energy go? For centuries, the idea of conservation had been a quiet comfort. You could watch an apple fall from a tree, and though its motion changed, the total energy, its potential above the ground, and its speed as it fell stayed the same. It was as if nature kept perfect counting books, where every motion, every light beam, every spark was recorded and balanced to the last decimal. But Einstein's new theory, the general theory of relativity, changed the very paper those books were written on. In his equations, energy wasn't a neat little number you could add up. It was spread across the curved geometry of the universe itself, folded into the way matter shaped space, and space guided matter in return. At first, Einstein thought he could find where it all hid. He tried to define a mathematical object, something that could track the energy of gravity, the way a thermometer tracks heat. But every time he tried, the definition broke when he switched frames of reference. What looked like energy in one perspective simply vanished in another. It was as if the universe refused to say exactly where its power was stored. He wrote to his colleagues in frustration. One of them, the mathematician David Hilbert, tried to help, exploring a set of equations called the Bianchi identities. patterns that seemed to promise energy conservation, but only in an empty universe, one without stars, planets, or people. That wasn't good enough. Einstein's equations had to work for a universe filled with everything, from the glow of the sun to the pull of a falling apple. And so, as he wrestled with the mathematics, he found himself circling a deeper question. What does it even mean for energy to be conserved if time itself can change? Years earlier, when he worked as a patent clerk in Bern, Switzerland, Einstein had discovered what he later called the happiest thought of his life. He imagined a man falling from a rooftop, not in panic, but in pure curiosity. In that instant of free fall, the man would feel weightless. A ball dropped beside him would hover. His tools, his hat, even a coin slipping from his pocket would float beside him, as if the pull of earth had vanished. From the man's perspective, gravity no longer existed. What he felt wasn't a force at all, it was simply motion through a curved space-time. That thought, so simple and human, became the seed of the equivalence principle, one of the cornerstones of general relativity. It told Einstein that gravity and acceleration were two sides of the same coin. If you were in a sealed rocket accelerating through space at 10 meters per second each second, the same acceleration as falling on Earth, you would feel a steady pull beneath your feet, indistinguishable from gravity itself. This realization changed everything. Gravity was not a mysterious hand pulling objects together. It was the shape of space-time telling matter how to move. And matter, in turn, told space-time how to bend. But if the fabric of the cosmos could bend, twist, and stretch, could energy still be truly conserved? Or was conservation only an illusion that worked in flat, simple spaces, like a rule from an older universe that no longer applied? To make his theory work, Einstein had to use something called tensors, mathematical structures that could describe not just points, but directions, surfaces, and the way they curved. A tensor, in its gentlest description, is like a multi-layered compass. Wherever you stand, it tells you how something changes if you move forward, backward, sideways, or even through time itself. If space is flat, those directions remain steady, like arrows drawn on a calm sea. But in curved space they begin to twist, pointing inward near a planet, or outward across a cosmic void. Einstein's equations used tensors to weave matter and motion together. But when he tried to add up the total energy of that woven fabric, the numbers refused to settle. Each time he changed the viewpoint, as if tilting the universe by a degree, the so-called energy shifted shape. What one observer saw as energy, another saw as none at all. He even invented something called a pseudo-tensor, a sort of mathematical bandage to describe the energy of gravity. But the moment he transformed the coordinates the bandage tore, it didn't behave like a real tensor. It changed when you looked at it differently, breaking the very principle of general covariance, the rule that says the laws of physics must look the same no matter where or how you stand. To Einstein, this was intolerable. The laws of nature had to be universal, no special perspectives, no hidden frames. But to Noether, who would soon enter the story, that struggle itself contained the answer. She saw what Einstein couldn't. His theory was too beautiful, too symmetrical to cling to an old law of conservation that demanded a static, unchanging stage. If space-time itself is alive, stretching, curving, expanding, then insisting on perfect energy conservation is like demanding a heartbeat that never changes its rhythm. You can only keep perfect time in a universe that never evolves. Einstein's mistake wasn't mathematical, it was emotional. The desire to hold on to an ancient certainty. Noether, with her quiet clarity, was ready to show him that physics didn't need to cling to that certainty at all. She would prove that conservation itself was a gift of symmetry, a gift that exists only as long as the universe chooses to stay still. But when the cosmos begins to move, when time itself starts to unfold, that gift softly slips away. As we follow the thread a little further, we'll step into her world, a world of mirrors, rotations, and hidden balance, where the secret of energy's disappearance finally takes form. If history were fair, the name Emmy Noether would shine as brightly as Einstein's. But history often favours the loud and the visible, while true revolutions sometimes begin in quiet rooms, where a woman sits surrounded by papers, her mind tracing the invisible threads that hold the universe together. In the early 1900s, Noether was not supposed to be there at all. The universities of Germany were temples of logic and precision, but for women, the doors were almost closed. She was allowed to attend lectures only by special permission, not as a student, but as a silent observer. Yet, as she listened, she began to see patterns that even her professors missed, the kind of patterns that live not in equations themselves, but in the spaces between them. She noticed something profound about the way nature hides its simplicity. It repeats itself. The same curve, the same ratio, the same invisible rhythm shows up again and again. In geometry, this repetition has a name: symmetry. To most people, symmetry is simple: a butterfly's wings, a snowflake, a reflection in water. But to Noether, symmetry was not just about shapes. It was the language of truth itself, the rule behind every rule. When you hold up a mirror to a triangle and see it unchanged, you've found a mirror symmetry. When you rotate a perfect circle by any angle and it still looks the same, that's rotational symmetry. But Noether went further. She asked, what if the symmetry isn't something you can see? What if it's hidden in the way equations behave when you shift, turn, or stretch them through space and time? For example, she noticed that if you move an experiment from one location to another, say from this room to the next, the results stay the same. The laws of physics don't care where you are. That simple fact, sameness under movement, is a kind of symmetry, and it gives rise to a physical truth we all know. Momentum is conserved. She then imagined spinning that experiment instead of moving it. Again, the rules stayed the same. That rotational symmetry leads to another conservation law: angular momentum. A spinning top stays spinning because the universe doesn't prefer one direction over another. But her most beautiful insight came when she asked about time. What if you do the same experiment today and tomorrow, or a second from now, or 1,000,000 years later, and the laws of physics remain unchanged? That kind of symmetry, where time itself is uniform, gives rise to one of the most sacred principles of all: the conservation of energy. It was a breathtaking connection, a bridge between symmetry and stability. To explain it to her colleagues, Noether used a new kind of mathematical language, one based on something called the action principle. Imagine the universe as a great traveller, always choosing the path that requires the least effort. A falling apple, a planet's orbit, a beam of light bending through glass. All follow the route that minimizes a certain quantity known as action, a blend of motion and potential. Noether realized that if the laws of nature stay the same while you shift time forward by a small amount, even just an instant, the overall action of the system doesn't change. In her notation, it was written as something like, the change in action over time equals 0. But you don't need symbols to feel what it means. When the rhythm of time stays steady, the universe doesn't lose or gain energy. It simply flows. She then took that quiet insight and made it universal. If the world looks the same when you move it, momentum stays constant. If it looks the same when you turn it, angular momentum stays constant. If it looks the same when you slide time forward, energy stays constant. Every law of conservation, everything we believe about stability, was suddenly revealed to be born from symmetry. For centuries, scientists thought of conservation as a rule engraved into reality. Noether showed it was more like a reflection, a consequence of how the universe chooses to stay consistent. When she shared her findings with David Hilbert and Albert Einstein, they immediately recognized their importance. Einstein later wrote that Noether's theorem was a monument of mathematical thought, but even he didn't yet grasp the full depth of what she had uncovered. Because what Noether discovered went beyond equations. She had found a new kind of logic, one that said, if you want to find what never changes, look for what can move freely without breaking the rules. Her theorem was like a key that unlocked the hidden architecture of physics. It explained why energy seems to be conserved in most cases, and why, in an expanding universe, it can fade away. To understand this, imagine the universe as a great clock. If its rhythm never falters, if every tick is perfectly even, then energy remains constant. But if the clock itself is stretching, slowing, or bending with age, then the energy it measures can no longer stay the same. Noether saw this long before cosmologists did. She realized that conservation is not absolute. It is conditional. It holds only when the stage of time remains still. But our universe is no such stage. It's a play that writes itself as it performs. And in that play, time is not a fixed backdrop. It's a changing fabric, weaving new space as it goes. In her second great insight, she extended her theorem into curved spacetime, where the geometry itself shifts from point to point. Here, her mathematics revealed something even subtler. When the symmetry is local, meaning it holds only in small regions, conservation transforms into something softer, a continuity equation. Translated into an image, it's like water flowing through a vast network of pipes. In each short section, the amount of water entering equals the amount leaving. Nothing is created or destroyed. But across the whole system, tiny leaks and expansions change the total flow. That's how energy behaves in an evolving universe. Locally it is conserved. Globally, it drifts. Einstein's equations hinted at this but couldn't articulate it. Noether's theorem made it precise and poetic. It told physicists, you can have a changing universe, or you can have perfect conservation, but you can't have both. It's a quiet revelation, almost spiritual in its simplicity. The universe is not a sealed box where numbers stay constant. It's a living pattern, always shifting, always breathing. And from that breath, from that slow imbalance, time itself begins to flow. As we drift further into the story, this idea of change, this gentle loosening of order, will guide us into the next great mystery. Because if Noether's symmetry explains how energy seems to fade, then the next question is why the universe keeps letting it fade. To find that answer, we must meet the one principle that refuses to stop growing: entropy, the silent engine of time. There is a kind of music beneath everything, not the kind that comes from strings or wind, but from the universe itself, a rhythm of balance and repetition, a quiet symmetry that underlies all motion. Emmy Noether had found its sheet music. She had shown that when the rhythm remains steady, the melody of nature plays perfectly in tune. But when the rhythm changes, when time stretches or space expands, the notes begin to drift. The harmony fades. Imagine the universe as a grand orchestra. Each instrument is a force of nature. Gravity, light, magnetism, the slow dance of atoms. Together, they perform the same composition, guided by invisible timing. The score never says, keep energy or keep momentum. Instead, it says, play your part the same way, wherever and whenever you are. The constancy of the music, its symmetry, creates the illusion of conservation. In this cosmic performance, moving something across space without changing the sound gives us momentum. Turning it without breaking harmony gives us angular momentum, and playing the tune in perfect time gives us energy. If the beat of time is steady, energy appears constant. If the rhythm wavers, energy softly transforms into something else. This is Noether's great revelation turned into poetry. Conservation is not a rule imposed on the universe. It's the echo of its rhythm. To sense how deep that idea runs, imagine a child on a swing. As long as you push at the same moment each time, matching the swing's rhythm, the motion continues easily without loss. The symmetry between the child's arc and your timing keeps the motion alive. But if the timing shifts, if your pushes fall out of sync, energy slips away and the swing slows. The same thing happens on the scale of galaxies. The timing of the universe, the rhythm of its expansion, is no longer steady. So the energy that once kept light racing across space slowly fades. Not because it's being stolen, but because the tempo itself is changing. Noether's insight meant that every law of physics was part of a pattern, a tapestry woven from symmetries. Shift space, and you discover momentum. Turn the world, and you uncover spin. Slide through time, and you meet energy. Each conservation law was not separate, but a verse in a larger song. She expressed it in equations, of course, lines of symbols that curve and repeat like notes on a staff. But even without numbers, you can feel what she meant. The universe doesn't cling to its quantities, it clings to its structure. When that structure holds, the rules stay the same. When it bends, something beautiful and irreversible begins to happen. This connection between symmetry and stability is everywhere, from the smallest particles to the vastest clusters of stars. The same idea that keeps a spinning top upright also keeps the planets orbiting, the galaxies rotating, the particles inside atoms bound together in dance. It's easy to take this stability for granted. We live in a part of the cosmos where time behaves well, where each second follows the last like pearls on a string. But in the long story of the universe, that steadiness is not eternal. It's a temporary kindness. The deeper you look, the more fragile that kindness appears. Galaxies drift apart. Light stretches into longer, softer waves. The symmetry of time begins to slip, and when that happens, Noether's link between symmetry and energy gently loosens. Einstein once described space-time as a kind of fabric, flexible, alive, able to bend under mass and motion. Noether revealed the deeper truth. The fabric doesn't just bend, it sings. And its song determines what stays constant and what fades away. In her equations, time translation symmetry, the idea that the laws of nature stay the same from one moment to the next, gives rise to energy conservation. But let's translate that into simple words. It means that if the cosmic clock ticks evenly, every motion, every photon, every atom carries the same rhythm. Energy can't be lost because the music of time never skips a beat. But the moment that clock begins to stretch, even slightly, its rhythm no longer fits the old song. The melody wavers. Energy doesn't vanish, it simply changes form, dissolving into the wider rhythm of the universe. It's like listening to a note on a violin fade as the air around you expands. The sound doesn't disappear. It just stretches until it becomes silence. In a static, frozen universe, energy would remain perfect, but time would be meaningless. Everything would stand still. There would be no change, no decay, no breath, no thought. Energy conservation, absolute and eternal, would be the same as death. Instead, our universe chose imperfection, and through that imperfection, movement was born. The slow drift of galaxies, the heat of stars, the ticking of clocks, the beating of hearts, all arise because the universe allowed its rhythm to wander ever so slightly from perfect symmetry. That drift is not a flaw, it's creation itself. And so, when you think of energy, don't picture a solid number, something trapped in equations. Picture it as a current in an endless river. The water flows, turning stones and wheels as it passes. You can measure its force here, in this bend, in this valley. But across the whole landscape, the flow changes, joining new streams, losing itself to the sea. Locally, the water conserves its volume. What flows in flows out. But globally, the currents shift and the pattern of flow evolves. Energy in our universe behaves the same way. Locally, it balances. Globally, it drifts with the expansion of space. It's easy to think of the cosmos as a grand clock, precise, mechanical, obedient. But Noether showed it's closer to a heartbeat, living, irregular, full of quiet meaning. The conservation of energy, so often spoken of as a law, is not a commandment written into stone. It's a relationship, a whisper between time and symmetry, an agreement that holds only as long as both keep their rhythm. And when that rhythm changes, the whisper becomes a sigh, soft, fading, beautiful. This is the hidden rhythm beneath all things, the one that lets the universe evolve, that lets time move forward, that lets every star burn and fade. If we follow the thread a little further, we'll find that this fading, this gentle loss, is not random at all. It has direction, purpose, and consequence. It shapes the flow of time itself. The next step in our quiet journey leads us to the secret that gives time its arrow, the slow, unstoppable rise of entropy. If you could step outside the universe and look back at it, not at its stars or galaxies, but at the fabric itself, you would see something extraordinary. The stage on which everything unfolds is not fixed, it's expanding. Every second, space itself stretches a little farther apart. It's hard to feel from where we sit. The distance between you and the lamp beside your bed doesn't grow, and the cup of tea on your table doesn't slowly drift away. Gravity and molecular bonds hold them tight. But between galaxies, where the pull of matter is faint, the fabric of space gently lengthens, like a vast breath inhaling through eternity. This expansion was discovered a century ago, almost by accident. Astronomers studying the light of distant galaxies noticed something peculiar. The farther away a galaxy was, the redder its light appeared. It wasn't because the galaxies themselves were red. It was because the light waves had stretched during their long journey through expanding space. You can imagine it like this. Picture a beam of light as a line of tiny waves, each one cresting and dipping in rhythm. As the universe expands, those crests move apart. The waves lengthen, their colour shifting toward red. The same number of waves still exist, but they've been spread thinner across the widening cosmos. In ordinary terms, you could say the light loses energy, but Noether would tell you that's not quite right. The energy doesn't go anywhere. It's just that the universe no longer gives that word the same meaning. The concept of energy depends on the rhythm of time, and when time itself stretches, the measure of energy bends with it. If a photon left a star billions of years ago, bright and blue, by the time it reaches us it has become soft and red, its colour cooled by the expansion of space. Its energy has faded, not because it was spent or absorbed, but because the very tempo of the universe has changed. The cosmic clock has slowed its beat. For a long while, scientists believed this expansion would eventually slow down. They thought that gravity, the quiet pull of all matter, would gradually rein it in, maybe even reverse it one day. But in the 1990s, astronomers measuring distant supernovae found the opposite. The expansion wasn't slowing, it was accelerating. Space itself was speeding up, pulled apart by something unseen, something we now call dark energy. We don't yet know what dark energy truly is. It's not like sunlight or magnetism. It doesn't push or pull in the usual sense. It simply adds more space between things, and as it does, it deepens the riddle of energy. The total energy of the universe seems to be increasing as the stage grows larger. More empty volume, more vacuum energy, as if the cosmos were creating something from nothing. But Noether's theorem whispers a simple explanation. If the universe has no true time symmetry, if every moment is a little different from the one before, then there's no reason to expect energy to stay fixed. In an expanding cosmos, the rhythm of time is not constant, so the melody of conservation gently drifts. You can think of it like an old vinyl record that's slowly warping as it spins. The music still plays, but the pitch changes slightly. Notes stretch, rhythms wander. What was once a clear tune becomes a slow, beautiful distortion. Our universe is that record, and its music, the patterns of energy and motion, shifts as the grooves stretch beneath it. For everyday life, this change is imperceptible. The equations of physics still hold perfectly in our local patch of space. Your heartbeat doesn't slow because galaxies drift apart. A thrown ball still arcs and falls just as Newton promised. On short time scales, time seems even, and energy appears conserved. But when you look across billions of years, when you watch the great expansion unfold, you begin to see the quiet symmetry. The notes are still there, but their meaning is changing. The cosmic tempo is drifting, and the energy of light and motion fades softly into that slow dance. This change gives rise to something we call cosmic redshift, the reddening of all light as it moves through the expanding universe. Imagine a violinist playing a clear high note in a small room. If the room were to slowly stretch while the sound reverberated, the note would deepen. It would lower in pitch, not because the violinist played differently, but because the space through which the sound travelled grew wider. The same happens with light. The room is the universe, and its expansion gently lowers the energy of every photon passing through. It's an elegant example of how the universe bends the rules, not by breaking them, but by changing the stage on which they play. And yet this idea that the energy of light can fade away without going anywhere still feels unsettling. We are creatures who like to keep accounts. We want to know where things go to balance the books. But the universe doesn't keep human accounts. It balances itself through structure, not through numbers. What Noether discovered, and what modern cosmology confirms, is that the deeper the symmetry, the gentler the rule. The universe conserves not things, but relationships. The ratios between patterns, the harmony of motion and form. When that harmony shifts, we call it evolution. In that way, energy's apparent disappearance isn't a failure of physics. It's a reminder that physics itself is alive. The laws we hold dear are not rigid commandments, but living correspondences, agreements between space, time, and motion that evolve as the universe does. Even Einstein, for all his brilliance, could not quite accept that. He once said he could not believe God played dice with the universe. But in another sense, perhaps the cosmos does play dice, not to gamble, but to keep the game moving, to keep the rhythm from falling silent. As we sit under the slow expansion of the stars, we're carried by this same stretching fabric. Every breath you take, every second that passes, happens in a universe that is quietly growing larger, older, and softer. And though the change is almost invisible, it defines everything we know. The energy that lights your room tonight came from processes that depend on this delicate imbalance, on a cosmos that never quite repeats itself. And so, when we speak of conservation, perhaps we should remember Noether's truest gift, the realization that permanence itself is an illusion, and that the universe's most profound beauty lies in its willingness to change. If we follow the thread a little further, we'll see that this gentle expansion, this gradual loss of energy's meaning, is not just about light or motion. It's the foundation of something deeper, the arrow of time itself, and the quiet rise of entropy, the principle that gives every story, even the universe's, a beginning, a middle, and an end. If you could trace every current of energy in the universe, every flicker of light, every pull of gravity, every faint ripple of heat, you might imagine it as a network of invisible streams flowing through space-time. Each star would be a bright fountain, spilling photons outward, each atom a tiny whirlpool, exchanging energy with the space around it. Together, they form the great circulation of existence. Now imagine that this entire network is made not of pipes, but of the fabric of the universe itself, flexible, stretching, full of subtle curves. At small scales, the water seems to move perfectly. Energy flows in, energy flows out, nothing appears lost. But when you zoom out far enough, you begin to see tiny seams in the fabric. The flow doesn't loop perfectly anymore. There are slow leaks between the threads, not breaks, not tears, but gentle shifts where the fabric itself gives way. This, in essence, is what Noether's second theorem revealed. It's the realization that in an evolving curved universe, energy is not a fixed total you can simply count up. It's more like a song played across instruments that are themselves slowly changing shape. Locally, the notes stay true. Globally, the harmony drifts. Einstein's equations, those graceful lines of geometry and gravity, already hinted at this. They showed that matter tells space how to curve, and space tells matter how to move. But when physicists tried to define where energy existed within that curvature, the answer dissolved. The equations balanced, but the meaning of balance changed from one patch of the universe to another. Noether found the bridge between the two worlds. She showed that what remains constant is not a single, global number, but a pattern of flow, a continuity equation. In everyday life, you already know this principle. Picture a river running through a narrow valley. If more water enters the valley than leaves it, the river rises. If more flows out than in, it falls. The amount of water in that section changes, but not because the universe created or destroyed it, only because the flow shifted upstream or downstream. Mathematically, physicists write this as the rate of change in one region equals the difference between what flows in and what flows out. But you don't need the symbols to feel it. It's the same rule that governs clouds and wind, heat and breath. It's the reason your lungs don't run out of air. The flow in matches the flow out, keeping you alive in the middle of a constant exchange. Noether translated this principle to space-time itself. She showed that for every small region in the universe, the same kind of balance holds. Energy may move from one patch to another, but in that small region, it behaves exactly as expected. What goes in must come out. It's only when you link these regions together, across the vast distances of curved space, that the picture begins to change. The curvature of space-time creates subtle mismatches, like the cracks between stones in an old fountain. Through those gaps, energy slowly leaks between regions, not lost, but transformed into the geometry of space itself. To understand it intuitively, think of the universe as a vast elastic sheet. When a heavy star sits on that sheet, it bends downward. If the sheet were to stretch while the star stayed still, some of the energy of its motion would go into that stretch. The star would seem to slow, not because it lost power, but because the stage beneath it was expanding. The energy went not into heat or light, but into shaping space. This is the cosmic leak, the gentle trade between motion and geometry. Noether's continuity equation captures this trade perfectly. Locally, energy still obeys the familiar rules. What enters a point must leave it. But globally, when you include the curvature of space-time, the way the fabric flexes, the total sum no longer stays constant. The universe isn't breaking its own laws, it's simply playing a more intricate version of them. Imagine again the water flowing through pipes. At first, the pipes are rigid. The flow inside is conserved. Then, one day, the pipes themselves begin to swell and shift. Tiny cracks appear, and water seeps into new paths. The total amount of water hasn't disappeared, but your definition of inside and outside no longer holds. In general relativity, the same thing happens. Space-time itself participates in the flow. It's as if the universe is not just the stage where energy moves. It's also an actor in the play. And like any living actor, it changes the meaning of the story with every gesture. When physicists try to calculate the total energy of the universe, they run into this paradox. You can measure energy locally, around stars, galaxies, or even clusters of galaxies, and the numbers make sense. But when you try to add everything together, the concept dissolves. In an expanding cosmos, there is no universal bank account for energy. The balance depends on where and when you measure it. This may sound unsettling, but it's not chaos, it's elegance. The universe isn't wasting energy, it's redistributing meaning. Think of a candle burning in a dark room. Its wax melts, the flame flickers, heat spreads into the air. If you only look at the candle, energy seems to vanish. But if you include the room, the warmth in the walls, the light reflecting off surfaces, the balance holds. Now imagine that the room itself is slowly expanding, its walls moving farther apart. The warmth stretches into new space. The candle fades faster, not because the flame weakened, but because the room's boundaries have changed. That's our universe, a single candle burning in an ever-expanding room. Noether's insight doesn't make energy less real. It makes it more alive. Conservation is no longer a fixed law carved into stone. It's a conversation between motion and the shape of time. And perhaps that's what makes the universe feel so human. We too are shaped by a kind of continuity equation. We take in sunlight, air and food, energy from the stars, and release it back as warmth and breath. Nothing is truly lost. It just changes where it lives. In the same way, the cosmos itself breathes. Energy flows through its lungs of space and time, shifting gently with every expansion, every ripple, every new birth of stars. And this breath, this soft, continuous exchange, sets the direction for everything that happens next. Because when energy spreads, when light stretches, when motion diffuses, something deep and irreversible begins to stir. Time itself starts to flow in one direction. Our quiet exploration now turns to that direction. The slow, invisible current that guides every change and every heartbeat in the universe. Entropy, the one quantity that only knows how to grow. There's a strange comfort in rules that never seem to break. When you drop a ball, it falls. When you light a match, it burns. In our daily world, everything appears steady, dependable, governed by invisible hands that always keep score. We call those hands the laws of physics, and they are so reliable that we often mistake them for truth itself. But what Noether revealed, and what the universe quietly reminds us, is that these laws are not absolute commandments written across the stars. They are local agreements. They work beautifully in small regions, in familiar times and spaces. Yet beyond those boundaries, they begin to shift, like music played on an instrument that slowly changes its tuning. In your room, the rules of energy are precise. You can heat water on a stove, and every bit of fuel burned becomes warmth or motion or light. Nothing vanishes. The system balances perfectly. But when we lift our eyes to the night sky, we're no longer dealing with a closed room. The walls are gone. The boundaries themselves are expanding, and the laws that once seemed unbreakable begin to soften at the edges. Einstein's general theory of relativity gave us the first glimpse of this flexibility. It told us that gravity isn't a force pulling objects together, but a curvature, a gentle bending of the stage they move upon. That bending can change from place to place, just as the slope of a hill changes as you walk. So, if the geometry of the universe changes, the flow of energy across it changes too, and yet, remarkably, the local balance still holds. This is one of the most delicate miracles of physics. In any small patch of space-time, you can still draw a tiny boundary, an imaginary bubble, and say, within this bubble, energy behaves. It flows in, it flows out, and nothing is truly lost. That's Noether's continuity equation in its simplest human form. But when you zoom out and try to connect one bubble to another, the picture begins to shimmer. The rules that work so neatly inside each bubble no longer align perfectly across the whole. The spaces between the bubbles curve, stretch, and sometimes twist. And through those tiny mismatches, energy slowly seeps from one region to another, becoming part of the shape of the universe itself. It's not that the cosmos breaks its promises, it just keeps redefining what the promise means. Imagine for a moment that you're sailing across a calm sea. The water beneath your boat is smooth, the horizon clear. You can measure your speed and direction easily. But as you travel farther, you begin to notice that the water itself is moving, carrying you along with unseen currents. Locally, you're still following the rules of motion. Globally, though, you're part of something larger, an ocean that decides its own paths. Energy in the universe behaves much the same way. Locally, it obeys Newton's precision and Noether's symmetry. Globally, it drifts with the tides of space-time. When physicists realized this, it changed how we think about conservation itself. It's not that energy disappears, it's that its identity depends on context. What you call energy here, in this patch of the cosmos, may look entirely different to an observer far away, where space-time curves differently. It's a little like hearing music through walls. In one room the melody sounds crisp and bright, in another it's muffled and slower. The song hasn't changed, only the way the space carries it. That's why physicists talk about local conservation instead of global. The laws remain perfect within any region small enough that space-time looks flat. But when you move from one curved region to another, the definitions of time, distance, and even energy shift. In everyday life, these shifts are so tiny we never notice them. You could live and die without ever sensing the universe's curvature, just as a flea on an orange might never realize it's standing on a sphere. But over cosmic distances, across billions of light years, those tiny differences accumulate. The universe stretches the meaning of energy, one photon at a time. Even light, which travels at the highest possible speed, isn't immune. As it crosses the expanding cosmos, its waves lengthen. Its once blue glow turns red, its energy fading in step with the growth of space. The light doesn't grow weaker because something took it away. It fades because the rhythm of time itself has changed between where it started and where it ends. This is one of those moments where physics and philosophy gently intertwine. What we think of as law is not an iron cage, but a conversation between the universe and itself. And Noether's theorem is that conversation, written in the language of symmetry. It tells us that every conserved quantity, momentum, energy, charge, is a kind of echo. Each exists because the universe allows some motion, some rotation, some transformation that leaves its essence unchanged. But when the universe itself transforms, when the symmetry of time falters, those echoes fade. They don't vanish, they evolve. Einstein saw this too, though at first he resisted it. He believed the universe must somehow keep perfect track of its energy, even as it curved and stretched. He imagined that perhaps the missing energy hid in the gravitational field, that the bending of space itself carried it. But Noether's insight was deeper. She showed that energy conservation depends entirely on the uniformity of time. Without that uniform rhythm, the idea of a global ledger simply stops making sense. The revelation was quiet but profound. It meant that the universe could change without contradiction. It could expand, cool, and evolve, all while remaining consistent within itself. It didn't need an external bookkeeper to balance the equations. The balance was built into the way change happens. In this way, Noether gave the cosmos permission to breathe, and this breath, the steady expansion, the local perfection within global imperfection, became the bridge between Einstein's geometry and the arrow of time. You can picture it as a mosaic of tiny clocks scattered through the universe. Each one ticks perfectly in its own region, but because the fabric between them is curved, their ticks drift slightly out of sync. Over millions or billions of years, those tiny differences accumulate. creating what we experience as time's direction. In your everyday life, this arrow is so natural you never question it. You pour milk into coffee and it mixes, never unmixes. You grow older, not younger. The past feels solid, the future uncertain. But beneath all of this, what truly gives time its direction is this gentle asymmetry, this slow leak of order into curvature, of energy into space. It's a subtle thing, almost invisible, but it's what turns a static universe into a living one. Without that imbalance, nothing would ever happen. There would be no change, no motion, no life. And so, from the smallest atom to the grandest galaxy, the same truth echoes. Perfection is stillness, and stillness is death. The universe chose instead to move, to expand, to trade its symmetry for vitality. As we drift further into the story, we'll leave the geometry of space behind for a while and turn our gaze toward time itself, the quiet current that flows through everything. And we'll find that this current has a name, a pattern, and a purpose. It's called entropy, the slow, graceful unravelling that allows the universe to keep going. There's something deeply moving about the way light travels. It leaves its birthplace, the furious heart of a star, carrying a memory of that moment in its colour. The bluer the light, the more energy it holds, the younger and more restless it seems. The redder the light, the gentler, older, more weary. And across the vast distances of space, that colour begins to change. Every photon that reaches us has a story, written not in words but in wavelength, the distance between one crest of its wave and the next. In a laboratory, we can measure this precisely, in tiny fractions of a metre so small that even a grain of sand seems enormous by comparison. But when that same photon leaves a galaxy billions of light years away, the space it travels through is no longer fixed. The fabric between the crests of its wave slowly stretches. What began as a bright blue note arrives as a soft red whisper. This is what astronomers call redshift, but the word barely captures its beauty. It's the sound of the universe breathing out. Imagine, for a moment, you're listening to music through a record player, and as the record spins, it begins to warp, expanding ever so slightly. The melody stays the same, but the pitch drifts lower, the notes stretch. That's what happens to light as the cosmos expands. The tune of the photon doesn't stop, the stage beneath it grows. From Earth, we can see this cosmic stretching written across the sky. The most ancient light, the afterglow of the Big Bang, now arrives as a faint hiss of microwaves. Those photons were once fierce, blazing with the energy of newborn creation. In the 380,000-year-old universe, they were visible light, blue and hot, shining like fire. Now, after 13.8 billion years of expansion, they have cooled by a factor of 1,000. What began as brilliance has become almost silence. You might ask, where did all that energy go? It's tempting to picture it as loss, as if the universe were an old lantern slowly running out of fuel. But in truth, the energy didn't go anywhere. The very definition of energy changed. In physics, energy depends on frequency, on how many wave crests pass a given point each second. But when space itself expands, those crests are pulled farther apart. The rhythm slows, and so does the measured energy. In equations, scientists might write that energy is proportional to frequency, a simple relation discovered by Max Planck more than a century ago. But you don't need the symbols to feel it. Just imagine a pendulum swinging slower and slower as its string lengthens. The pendulum hasn't lost its motion. It's obeying a new rhythm set by the length of the string. So, as light crosses the widening cosmos, it doesn't shed energy like a tired traveller dropping baggage. It adjusts to the new tempo of time. Its wavelength grows, its pitch deepens. The photon becomes part of the music of expansion. When we look at a distant galaxy, its light carries both distance and history. A faint red smear on a telescope image tells us that we're not seeing the galaxy as it is now, but as it was billions of years ago, when the universe was smaller and the fabric tighter. Each additional stretch in its light's wavelength tells us how much the universe has grown since that photon began its journey. To human eyes, this change is invisible. Our senses are tuned to the narrow band of light that the sun emits most strongly. But to our instruments, the shift is undeniable. It's like finding fingerprints of time itself imprinted on every photon. If we think of the universe as a grand story, then each photon is a letter that has been pulled wider with age, the ink fading but never erased. And this isn't just a curiosity. It's proof that time is not the same everywhere, that even the act of measuring energy depends on where and when you're in the cosmos. To a being in the early universe, that same photon would seem fierce and blue. To us, it's mellow and red. We share the same light, but not the same moment. The phenomenon doesn't only affect light from galaxies, it touches everything that moves through space. A rock drifting through the expanding void, like the one we imagined at the beginning of our journey, gradually slows for the same reason. Its kinetic energy, the energy of motion, fades not because it meets resistance, but because the definition of motion itself changes as the cosmic stage expands. Noether's insight helps us see why this is natural. If the universe's symmetry and time were perfect, if every tick of the cosmic clock matched the one before, energy would remain constant. But the universe doesn't tick like that. Its clock is alive, stretching, slowing, quickening with the expansion. And so, energy too is alive. You can think of the photon's journey as a kind of aging. It begins its life energetic and compact, like a heartbeat racing with youth. As it travels, space stretches it thinner, and its frequency slows, like an old heart settling into calm rhythm. Nothing is lost, only the pace has changed. There's a quiet grace to that idea. Energy, in this view, isn't a treasure to be hoarded, but a rhythm that adapts to its surroundings. When the surroundings grow vast, the rhythm softens. It also means that when we gaze into the deep sky, we're not just looking outward, we're looking backward, through the changing rhythm of time itself. Every shade of red in those distant galaxies is a record of expansion. The farther the galaxy, the more the music has stretched, the older the universe's song. That song, faint though it is, connects us to the very beginning. The microwave afterglow that hums through space, what scientists call the cosmic background, is the universe's first lullaby still echoing after almost 14 billion years. It surrounds us even now, whispering through old radio receivers, through the static between channels. And within that whisper lies the story of everything that followed. The cooling of matter, the birth of stars, the rise of planets and life. All of it happened because the universe couldn't stay perfectly still, because symmetry broke just enough to let light stretch, to let energy shift, to let time flow. So when light forgets its colour, it's not forgetting at all. It's remembering where it came from, while learning how to live in a larger world. The redness of distant galaxies is not a loss, but a testimony that the universe grows, that time moves, that nothing remains unchanged. And in that quiet fading of light, in the way a brilliant blue becomes a soft crimson, we can almost hear the universe exhale, a sigh that began with the first dawn and has never quite ended. From here, the story opens into the question hidden inside that sigh. If energy can fade and light can stretch, what is the force that drives the universe to keep changing? What gives this vast, cooling expanse its direction, its one-way journey from brightness to stillness? To find that answer, we must turn to the secret that gives time its arrow, entropy, the universe's way of remembering the past while letting go of the future. If you step outside on a clear morning and feel the sunlight on your face, it's easy to think of it simply as warmth, as energy arriving from 93 million miles away. We call it sunlight, but that word feels far too small for what it truly is. The sun doesn't just send us energy, it sends us structure, order, and possibility. It sends us the rarest gift the universe can offer, low entropy. That phrase, low entropy, sounds cold and mathematical, but it describes something intimately familiar. It means the sun's light arrives full of potential, focused, bright, organised. Every photon, every particle of light carries a kind of precision. You can think of it as golden, threads woven tightly together, packed with order that can still be unwound into life, motion, and warmth. When sunlight strikes the ocean, it stirs the water into waves. When it touches a leaf, it becomes food and growth. When it warms your skin, it becomes the small miracle of temperature, molecules moving just a little faster than before. In each case, the sun gives the earth something more precious than energy. It gives it useful energy, energy that can be spent, transformed, and shared before it fades into stillness. But what do we send back into space? From orbit, the Earth glows faintly in the infrared, not golden, not blue, but soft red warmth. The light we return to the cosmos is dim, diffuse, and scattered in all directions. We take in concentrated sunlight and return it as a whisper of heat. We borrow golden threads of order and give them back as a warm sigh. That sigh, that quiet exhalation of the planet, is entropy. It's not destruction or decay, it's a transformation. It's how the Earth pays its rent to the universe for the privilege of being alive. Every second, the planet receives about 1,000 watts of sunlight per square metre on its surface, a steady flood of photons, each one carrying just the right amount of energy to stir atoms without tearing them apart. Plants capture some of it. Oceans absorb and reflect it. Clouds scatter it like music through mist. The rest becomes heat, radiating outward into the darkness. If you could see the Earth through the eyes of an infrared telescope, you'd see a sphere glowing softly in long, gentle waves, warmth flowing back into the void. That returning radiation carries almost all the entropy the sun's light once lacked. The exchange is profoundly unequal. The Earth sends out far more photons than it receives, about 20 times more, but each one is weaker, cooler, less organised. The total energy balances, but the quality changes. We turn a stream of order into a river of chaos, and from that imbalance everything happens. It's that difference between the tight order of incoming sunlight and the loose spread of outgoing warmth that allows life to exist at all. Imagine a house built beside a waterfall. The water at the top has potential. It can turn a wheel, power a mill, grind grain. But once the water falls, it spreads into a slow-moving pool, its energy spent. The waterfall doesn't create energy. It allows the difference between high and low to do work. The sun and earth are like that. The sun is the mountain spring, and earth is the mill turning quietly below. The photons streaming from the sun are hot and narrow, arriving in a focused range of wavelengths. The ones Earth sends back are wide and soft, spread thin across the spectrum. That spread is entropy. It's how the universe keeps its books balanced, even while allowing the brief miracle of structure and motion. It's humbling to realise that everything, weather, wind, life, even thought, exists in the space between those two flows of light. You can trace the beating of your heart back to that same difference. The food you eat began as sunlight captured by plants. The air you breathe is the product of light-driven photosynthesis. Every spark in your brain is powered by the same low-entropy energy that once travelled from the surface of the sun, and all of it eventually is released back into space as heat. The atoms in your breath right now will one day carry that warmth away, radiating outward into the infinite dark. You are, in every sense, part of the planet's long exhale. But this process isn't wasteful, it's beautiful. It's the only way for the universe to evolve. If energy could never disperse, if sunlight never spread, if heat never drifted, nothing would change. There would be no weather, no chemistry, no life. The Earth's entropy output is not a flaw, it's the price of motion, the cost of life's persistence. So what we truly receive from the sun is not just energy, but the chance to spend it. The sun gives us order, and we use it to create complexity. Forests, oceans, civilizations, the laughter of children, the hum of cities, all of them temporary ripples in the great flow from hot to cold. And in the end, when all those ripples fade, the energy returns to the stars that gave it, smoothed and softened, like music settling into silence. You can picture the planet as a great engine of light and warmth. It takes in bright, narrow beams and exhales broad, soft radiance, and everything in between, the clouds, the oceans, the winds, the heartbeat of every living creature, is part of that transformation. The balance is perfect. The sun sends about 4 trillion watts of energy to Earth. The planet absorbs some, reflects some, and radiates back almost exactly the same total amount. But while the quantity is the same, the quality changes forever. And in that change lies the arrow of time, because every moment the Earth is taking structured energy, light that could do work, and turning it into diffuse warmth that cannot. The process never reverses. The sun will never receive its golden threads back again. Entropy isn't the end of things, it's the reason things can happen at all. As we breathe, the planet breathes with us, drawing in bright order, releasing soft chaos. The flow never stops, and though it feels steady, it's the slowest, most graceful current in existence, the invisible river of time. To understand where this idea began, how humanity first discovered that all motion, all warmth, all life must eventually pay this quiet toll, we have to return 2 centuries into the past, to a young man in France who once stood beside a steam engine and asked a question no one had thought to ask before: how does heat become motion? And with that simple question, he unknowingly uncovered the seed of entropy, the quiet principle that would one day explain not only engines and sunlight, but the flow of time itself. If you listen closely to the hum of the modern world, the wheels turning, the engines roaring, the electricity flowing through invisible veins, you can trace it all back to a single, quiet dream, born 2 centuries ago. It began in France with a young man named Sadi Carnot, who wanted to understand how fire could move the world. The year was 1813. Europe was still trembling from the echoes of Napoleon's wars. Trains had not yet conquered the land. The age of machines was just beginning to stir, and steam was its heartbeat. Carnot was the son of a mathematician and a general, raised in a world where ideas were both weapons and tools. As a young engineer, he looked at the steam engines of his time, massive hissing contraptions of iron and water, and wondered, what truly happens when heat becomes motion? It was a simple question, but no one had ever answered it completely. Everyone knew that you could burn coal, boil water, and drive a piston. But why it worked, or how much of that heat could be turned into motion, was a mystery. Carnot imagined the engine as a living thing, a system that breathed in heat, used it to move, and then exhaled it back into the air. To understand it, he had to picture how heat itself moved. In his day, people thought of heat as a kind of invisible fluid called caloric, something that could flow from one body to another like water through pipes. He didn't know yet that heat was really motion, the random vibration of atoms, but his imagination led him close enough to the truth to see the pattern beneath. He pictured 2 reservoirs, one hot, one cold. Between them, the engine would draw heat from the hot side. use it to push a piston, and then release what was left into the cold side. The cycle would repeat, over and over. In modern language, we call this the Carnot cycle, a perfect dance of heating and cooling, expansion and compression, a rhythm of transformation where every step is as efficient as nature allows. But you don't need the equations to feel its elegance. Imagine boiling water in a sealed pot, then letting it cool, then reheating it again, endlessly, each phase feeding the next. Carnot realized something extraordinary. The usefulness of heat, its ability to perform work, doesn't depend on the amount of heat itself, but on the difference between hot and cold. It's the contrast that matters, not the quantity. You can think of it like this. A waterfall can only fall if there's a difference in height between its beginning and end. If both the river and the valley were at the same level, no motion could ever occur. The same is true for heat. If everything were at the same temperature, there would be no wind, no storms, no life, just stillness. This was Carnot's revelation. That motion depends on imbalance, on the existence of difference. And from that simple truth came the foundation of thermodynamics, the science of energy, heat, and their transformations. In his imagination, Carnot built the perfect engine, a machine that could convert heat into motion without wasting any of it. He described it in the clean precision of mathematics, but the idea was as poetic as it was technical, a dream of perfect reversibility. In this perfect machine, every bit of heat taken in could be turned into work and then returned exactly as it was. No energy would be lost, no heat left behind. But real life had other plans. In the world of coal and iron, no piston moved without friction. No valve sealed perfectly. No system could breathe in and out without leaving a trace. Heat always slipped away, creeping into the surroundings as waste, a ghost that could never be called back. The dream of a perfectly reversible engine was as impossible as perpetual youth. Every action leaves a mark, every motion a little warmth behind. Still, Carnot's imagination was not wasted. His impossible dream gave physicists a way to measure what was possible. It set the upper limit for how efficient any engine or any process could ever be. That limit, though he couldn't name it, was the birth of a concept that would one day reshape our understanding of the entire universe: entropy. After Carnot's early death at only 36, others took up his ideas. A German physicist named Rudolf Clausius reinterpreted them decades later, in the 1850s, when scientists finally understood that heat wasn't a fluid but motion, the dance of countless invisible particles. Clausius gave mathematical form to the ghost Carnot had sensed. He said in simple words that heat always flows from hot to cold, and that every time it flows, a little of its potential to do work is lost, not destroyed, just spread out, thinned, softened. He called this gradual spreading entropy, from the Greek word trope, meaning transformation. But long before the equations, before the symbols, there was Carnot's quiet intuition. That difference drives motion, that imbalance makes life, and that perfection, though it may be beautiful, is also lifeless. It's a truth that reaches far beyond steam engines. Every process in the universe, from the fusion inside stars to the beating of your heart, follows the same rhythm. Energy flows from high to low, from concentrated to diffuse, from ordered to disordered, and in doing so it gives rise to motion, structure, and time itself. Carnot's dream was mechanical, but his legacy became cosmic. The sun, you could say, is the engine, the earth, the piston, the cold vacuum of space, the exhaust. And between them, everything that happens, every cloud, every ocean current, every life, is part of the same grand cycle. The next time you watch steam rising from a cup of tea, think of Carnot. What you're seeing is the same story that moves the stars, heat flowing downward, creating patterns as it fades. Every swirl in that steam is a signature of imbalance, a gentle reminder that nothing moves without a difference, and nothing changes without a little warmth being left behind. The dream of Sadi Carnot was not to build the perfect machine, but to understand why perfection is impossible, and why imperfection is what keeps the world alive. And to give that imperfection a name, to measure it, to describe its quiet inevitability, we must meet Clausius, the man who turned a whisper of warmth into a universal law. By the time Rudolf Clausius entered the story, the age of steam had matured into the age of ideas. Engines no longer amazed people just because they moved. Now, physicists wanted to know why they moved, and what invisible balance made their work possible. Clausius was a quiet man, methodical and careful, the kind of thinker who saw not just the spark of invention, but the faint glow that remained after the fire burned. Where Sadi Carnot had dreamed of a perfect cycle, Clausius wanted to understand why perfection always slipped away. He began, like Carnot, with something simple: heat flowing from a hot body to a cold one. Everyone had seen it: a pot warming on a stove, a cup of coffee cooling on a table, the way warmth seeps from your hands into a winter window pane. It was so ordinary that no one thought to question it. But Clausius saw in that simple act a quiet message from the universe. Why does heat always flow one way and never the other? Why can you warm a cold stone with your hand, but never make your hand colder by touching it? He realized that the old laws, those comforting equations of motion and force, were not enough to describe this gentle one-way street. They could tell you how things move, but not why they choose the directions they do. And so he looked closer. Inside every object, Clausius imagined countless tiny particles, atoms or molecules, bouncing, colliding, vibrating. Heat, he realized, was not a mysterious fluid after all. It was motion. When something is warm, its particles dance faster. When it's cold, they move slowly, like a song played at a lower tempo. In a hot region, the microscopic dancers jostle with energy. When they meet the slower dancers of a colder region, they share that energy until the rhythms match. Warmth becomes equilibrium, and equilibrium is peace. From this, Clausius began to see the pattern that Carnot had only glimpsed. The universe prefers balance, and every exchange of energy is a step toward it. But balance comes at a price: the loss of difference, the smoothing out of potential. To describe that loss, Clausius needed a new kind of quantity, something that measured not energy itself, but the way energy spreads. He called it entropy. He didn't mean it as a word of decay or despair. For him, entropy was a measure of transformation, of how energy changes form and loses its ability to do work. In one of his notes, he wrote that the energy of the universe is constant. The entropy of the universe tends toward a maximum. You don't need to see this as an equation to understand it. It simply means energy never disappears, but its usefulness fades. Imagine a room filled with the scent of perfume. At first it's concentrated. You can point to where the fragrance began, but leave it for a while and the scent spreads evenly through the air. The perfume hasn't vanished. It has only become impossible to gather back. The universe does the same thing with energy. Heat flows, light scatters, motion slows, not because the laws of physics fail, but because they are doing exactly what they must. The universe doesn't destroy energy, it relaxes it. In Clausius's world, this gentle spreading was as natural as breathing. When you exhale, the air from your lungs diffuses into the atmosphere. You can't call it back, but it doesn't vanish. It becomes part of something larger, part of the air that surrounds all living things. Entropy, in that sense, is not an end. It's participation. It's the way energy joins the rest of existence. Clausius gave entropy a symbol, one that scientists still use today, the letter S. But for our purposes, we can think of it as a measure of softness, the softness that comes when differences dissolve. He showed that when heat moves through a system, The change in this softness, this entropy, depends on how much heat flows and how warm the receiving body already is. The warmer it is, the less that heat can change it. The cooler it is, the greater the effect. In simpler words, the same breath of warmth means more to cold hands than to warm ones. And in this small truth lies a universal rule, one that applies not just to fire and engines, but to life and time itself. The universe moves toward evenness, toward a kind of cosmic comfort where every difference has been shared away. Clausius wasn't a poet, but his discovery has a poetic heart. It says that all things, from the smallest particle to the largest galaxy, are part of a single gesture, the slow unfolding from order to disorder, from sharp contrast to gentle harmony. Entropy is not destruction. It's the fading of structure into stillness, like ripples settling after a stone drops into water. The ripples don't vanish, they merge with the lake, and yet within that merging lies something miraculous. Every new pattern, every movement, every moment of beauty exist because of this flow. Without it, nothing would happen. If energy remained trapped, if entropy never rose, the universe would be frozen in a single unchanging note. But because entropy increases, because heat spreads and energy softens, the universe has motion, story, and life. Every sunset you've ever seen is a display of entropy, sunlight diffusing through the atmosphere, scattering into colours as it weakens. Every gust of wind is the result of warmth, leaving the equator and spreading toward the poles. Every heartbeat, every spark of thought is powered by the same one-way flow, from concentration to diffusion, from difference to balance. Clausius saw that this flow could never reverse itself spontaneously. The perfume never unmixes, the coffee never unstirs, the warmth never returns from cold to hot without help. The direction is fixed, like a current in a river that always runs downhill. He didn't yet call it the arrow of time. That phrase would come later. But he had found the mechanism that makes the arrow point forward. Entropy gave time its meaning, not through ticking clocks or turning planets, but through the simple fact that things change in only one direction. Everywhere you look, the same whisper of disorder hums beneath the world. It's in the fading heat of a candle, the crumbling of mountains, the quiet drift of galaxies. And that whisper is what gives us the present moment, the fragile, fleeting edge between what has spread and what still holds together. As we drift further into this story, we'll meet another mind, one who took Clausius's calm principle and gave it heart. A man who asked, if entropy always increases, how does the universe decide how fast to let go of its order? What makes one state more likely than another? His name was Ludwig Boltzmann, and for him, entropy wasn't just a rule of warmth. It was the mathematics of chance, the breath of probability behind time itself. If Clausius gave entropy its name, Ludwig Boltzmann gave it a soul. He was not content to describe what happens when heat flows or when order fades. He wanted to know why it happens, and whether time itself could be explained not by destiny, but by chance. Boltzmann lived in Vienna in the late 1800s, a time when science was both confident and restless. The great laws of physics seemed complete, polished, and eternal. Yet there was something missing, a connection between the smooth equations of motion and the rough, unpredictable texture of real life. He saw that nature, for all its elegance, was messy. Dust motes drifted in sunlight. Smoke curled and swirled in ways that no formula could predict. The same physical laws that allowed you to calculate the orbit of a planet failed to describe a spoon of sugar dissolving in tea. To bridge that gap, Boltzmann turned to probability, the mathematics of maybe. He realized that the world's apparent order and disorder could be explained not as contradictions, but as the natural balance of possibility. Imagine, he said, a simple system, a box filled with gas. You can't see the individual molecules, but you know they're there, bouncing, colliding, changing direction 1 billion times each second. To you, the gas looks uniform, quiet, still. But beneath that calm lies chaos, trillions of tiny particles following their own unpredictable paths. Each possible arrangement of those particles, each way they could be distributed, is called a microstate. There are countless microstates that all look the same to our eyes. When the gas is spread evenly through the box, it can be arranged in an almost infinite number of ways. When it's all crowded into one corner, there are only a few possible arrangements. Boltzmann realised that entropy measures not just the spreading of heat, but the number of ways the system can arrange itself without breaking the rules. The more possibilities, the higher the entropy. In his notebooks, he expressed this with a simple relationship between entropy and probability. Scientists later carved it onto his tombstone as an equation, but you don't need the symbols to feel what it means. It says, the greater the number of ways something can exist, the more likely it is to happen. Or, in softer words, nature prefers variety. That preference, that quiet tilt toward the likely, is what gives time its direction. It's not that the universe chooses disorder, it simply explores every possible state, and there are far more disordered ones than ordered ones. Imagine tossing a handful of dice. Once in a while, they all land showing the same number. That's order. Most of the time, though, they scatter into randomness. There's nothing mysterious about it. It's just probability. The dice aren't rebelling. They're simply more likely to fall into one of the many messy combinations than the few neat ones. The same principle governs everything from gases to galaxies. Entropy increases not because of magic, but because there are always more ways to be untidy than tidy. You can picture it in everyday life. When you stir cream into coffee, the mixture swirls into beautiful patterns for a moment, before blending into uniform brown. If you were to watch that process in reverse, the cream unmixing itself, separating into pure white streams, it would look impossible. Not because it violates physics, but because the odds against it are astronomically large. There are billions of ways for coffee to look mixed, and almost none for it to look pure again. Boltzmann used the same reasoning to describe heat flow, the collapse of order, and even the passage of time itself. For him, time's arrow didn't come from the equations of motion. Those equations work equally well forward or backward. The arrow emerged from statistics. The past is the direction of lower probability, the future the direction of higher probability. Entropy, then, is not a law written in stone, but a pattern of chance playing out over unimaginable scales. He sometimes compared it to dice rolling in the dark, not because the universe is random, but because it has so many options that it cannot help but seem random from our limited view. Think of a deck of cards. Shuffle it once, and you have one arrangement out of more than a number so vast it would take the universe itself longer than its lifetime to try them all. If you spread the cards on a table, you might find patterns, maybe a few in sequence, but you'd know that order was temporary. With every shuffle, the deck slides toward disorder, simply because disorder is what most of the arrangements look like. Boltzmann's insight was both profound and haunting. It meant that order is not natural, it's rare, fragile, fleeting. Every organised state, from the shape of a snowflake to the structure of your body, exists because of an extraordinary combination of circumstances. And over time, those circumstances always dissolve. He once said, almost wistfully, that if you waited long enough, unimaginably long, the molecules of air in your room could all drift into one corner by sheer chance. It's not impossible, it's just absurdly unlikely. The odds are so low that you would have to wait longer than the age of all galaxies combined to see it happen once. That simple truth, that the universe is ruled by probability reshaped everything. It turned entropy from a poetic metaphor into a physical principle. It explained why time moves forward, why heat flows from hot to cold, why life needs constant input from the sun to keep its improbable order. And it gave us a new kind of wonder, the realization that our existence is a statistical miracle. Out of all the countless ways matter could arrange itself, we live in one of the few that can think, feel, and look back upon the universe that made us. Boltzmann's work was not celebrated in his lifetime. Many of his peers resisted the idea that something as precise as physics could be governed by chance. To them, probability was not real. It was ignorance disguised as science. But time has a way of vindicating those who listen to its quietest rhythms. Today, every field from thermodynamics to cosmology echoes with Boltzmann's insight. The universe doesn't need intention to have order, it only needs time. And so, entropy, that rising measure of possibility, became not a symbol of decay, but of motion. It's the reason why cream swirls, stars ignite, and thoughts form. It's the reason we have memory, because the past, with its lower entropy, stands distinct from the future, which hasn't yet spread into all its possible forms. Entropy is the universe exploring itself, step by step, chance by chance. And in that exploration, time is born. As we follow the thread of the story further, we'll find ourselves facing a paradox. If everything tends toward disorder, how does life, this shimmering pattern of order, exist at all? How can something as improbable as a living being emerge and endure in a universe that leans toward chaos? To answer that, we'll turn to the sun once more, and to the way its light fuels the most delicate defiance of all, life's ability to create temporary islands of order within an ocean of increasing entropy. If you sit quietly beneath a tree on a summer afternoon and let the sunlight fall through the leaves, you're watching a miracle that's been running for nearly 4 billion years. It happens in silence, and yet it keeps every creature on Earth alive. The sunlight that touches your face isn't just warmth, it's order, freshly arrived from the edge of a star. But here's the puzzle. If entropy, the spreading, softening of energy, is always increasing, how can something as structured and delicate as life exist at all? How can forests grow, oceans swirl, and your heart keep beating in a universe that drifts unavoidably toward disorder? The answer lies in the way life borrows from imbalance. The Earth receives a constant flood of sunlight, bright, concentrated, low-entropy light. Every photon that leaves the sun carries information, direction, and possibility. When that light reaches Earth, something extraordinary happens. It doesn't simply heat the ground and vanish into space. It's captured, used, and reshaped. Plants, oceans, even the air itself become part of a vast, invisible circuit of transformation. A leaf, for instance, is not just green pigment and thin veins. It's a quiet machine built from improbable precision. When sunlight strikes it, the leaf takes in the light and performs a trick called photosynthesis. It breaks apart molecules of carbon dioxide and water, rearranges their atoms and builds sugar, tiny packets of stored energy. But the real magic isn't just in the chemistry, it's in the direction of the flow. The leaf takes low entropy sunlight, energy packed tight, full of potential, and transforms it into something the rest of the planet can use. The photons that enter the leaf are sharp and ordered. The energy the leaf releases is gentle and scattered. The balance of this exchange is what allows life to persist. You can think of it as a kind of cosmic economy. The sun sends a concentrated currency of energy. Life spends it freely, turning it into motion, warmth, and growth, and then returns it to the universe as soft, diffuse radiation. The total amount of energy stays constant, but the quality changes. Order becomes variety, structure becomes breath. It's easy to forget how delicate that trade is, Without the sun's low entropy light, the Earth would still radiate heat, but it would be like a planet breathing without lungs, exhaling what it can no longer replace. Jeremy England, a modern physicist, once suggested something bold, that life itself may be the universe's way of accelerating entropy. His idea was that matter, when exposed to energy for long enough, especially the right kind of energy, tends to rearrange itself into forms that dissipate that energy more efficiently. In other words, life isn't fighting entropy, it's helping it along beautifully. Imagine shining light on a puddle of molecules for billions of years. According to England's idea, those molecules might start forming shapes that channel energy better, absorbing light, releasing heat, building complexity that ultimately allows more energy to spread. That's life in its simplest, most cosmic definition. A self-organizing dance of atoms that helps the universe continue its great relaxation. It's a strange thought that every living thing, from bacteria to trees to you, is part of the universe's unfolding exhale. But it also makes existence feel deeply connected. We're not separate from the entropy around us. We are its expression, its artists, its gentle collaborators. Every time you breathe in, you take part in this cosmic exchange. The oxygen in your lungs was made in a star long before Earth existed. The carbon in your body was once part of a leaf that fed on sunlight. Each breath continues that chain. Concentrated energy transformed into warmth and motion. Order yielding to flow. Life, then, is not a rebellion against entropy. It's a pattern carved within it. A small region where order blooms only to help disorder spread more gracefully. You can see it everywhere once you start looking. A tree grows tall, converting sunlight into wood, fruit, and shade. Animals eat the fruit, releasing the stored energy as heat. Even the decomposition of a fallen branch continues the work, returning every atom to the soil and the air. The process never stops. It's all part of one grand current, flowing from the sun to space. Entropy increases, but along the way, the universe pauses to create beauty. From the narrow beam of sunlight to the vast field of infrared radiation leaving Earth, there's a journey of transformation. Each step, the blooming of a flower, the turning of a seed, the motion of your hands, adds a note to the universe's music of change. It's humbling to realize that all living things are temporary way stations for energy, shaping it briefly before letting it go. You might say, life exists to help the universe forget, to take sharp, structured sunlight and return it as soft warmth, scattered evenly into the dark. But that act of forgetting is where meaning arises, because in every instant of transformation, life makes form, it makes movement, it makes awareness. It turns invisible order into visible wonder. A photon that left the sun 8 minutes ago might now be resting in your hand as warmth, or in a blade of grass as sugar, or in your eyes as the colour of the sky. For that brief moment, it becomes part of your story, before moving on one step closer to the universe's long equilibrium. It's easy to think of entropy as a kind of doom, but through the lens of life, it's closer to art. Every living thing is a brushstroke of organisation painted on the canvas of time, vivid for a while, then fading, but leaving behind traces that make the whole picture richer. So when sunlight touches your face tomorrow, you can think of it as an invitation, a reminder that you're part of this cosmic trade. You're borrowing the universe's low entropy order for a moment, turning it into warmth, thought, and feeling before returning it to the great balance. It's a quiet kind of grace, isn't it? To exist not by defying entropy, but by participating in its unfolding. As we drift further into this story, we'll look more closely at that balance, how Earth itself acts as a perfect engine in this exchange, receiving the sun's bright energy and sending back its own calm radiation, turning imbalance into the rhythm of weather, growth, and time. If you could step back far enough from Earth, not just into orbit, but into the quiet distance of space where the planet is no more than a blue glimmer, you'd see something that looks alive. Clouds swirl like breath, oceans flash like eyes catching sunlight, storms rise and fade as if the world itself were exhaling. Beneath all of it, invisible but constant, is a steady rhythm, the exchange between sunlight and shadow, order and warmth, creation and release. This rhythm is not random. It's the sound of a perfect engine. Every second, the Earth receives a flood of energy from the sun, bright structured light. It absorbs that energy, transforms it, and then releases it as gentle heat. The process runs so smoothly that the balance is held for billions of years. It's the most elegant machine ever made, and it was not designed. It emerged. If we were to describe this in numbers, we could say that for every photon the Earth receives from the sun, it sends about 20 back into space. Softer, cooler, longer in wavelength. But you don't need numbers to understand it. You can feel it every time the day warms and the night cools. You can see it in the motion of clouds, in the flickering of leaves, in the whisper of waves. This constant trade, bright light in, dim heat out, is what keeps everything moving. The winds, the tides, the seasons, the patterns of rain and drought. All of it is powered by this slow, steady difference between what the Earth receives and what it returns. The energy we receive from the sun is highly ordered. Each photon carries a clear direction and a precise wavelength, like a note struck on a perfect instrument. When that light reaches Earth, it interacts with everything: molecules of air, drops of water, grains of sand, blades of grass, and scatters into countless directions. By the time it leaves again, the music has changed. The notes have stretched, softened, and spread. It's as if the planet takes the sun's bright melody and plays it back as a slow, warm hum. You can imagine the Earth as a great musical instrument, a glowing sphere that takes in sharp, focused sunlight and releases diffuse chords of heat. The balance between these two songs, the incoming and the outgoing, creates everything we know as weather and climate. When sunlight strikes the ocean, it stirs the surface, evaporates water, builds clouds. When that vapor condenses again, it releases heat into the atmosphere, driving winds and storms. The entire atmosphere becomes a circulating system of balance, a giant convection engine powered by the uneven warming of the planet's surface. Even hurricanes in their terrifying beauty are part of this balance. They are simply the Earth's way of redistributing excess energy, concentrated heat from the tropics carried toward the poles and released into the sky. A hurricane may seem like chaos, but it's actually a form of harmony, a necessary step in the great equation that keeps the planet's temperature steady. In this sense, the Earth is not a place where entropy is resisted, but where it's choreographed. The planet doesn't stop the flow of energy from order to disorder. It guides it, shapes it, delays it just long enough for life to bloom. Think of the planet as a middleman between two immensities, the burning sun and the freezing void. The sun provides an endless stream of high-energy, low-entropy light. Space offers a boundless sink where that energy can disperse. Between the two lies Earth, turning sunlight into motion, warmth, and life before releasing it onward. It's the same principle Carnot discovered with his steam engines. The Earth too runs on a temperature difference, the contrast between the sun's fiery surface and the cold darkness of space. Like any good engine, it extracts useful work from that gradient. And that work takes the form of winds, currents, lightning, growth, and thought. Even you sitting here are part of that conversion. The warmth you radiate into the air is sunlight transformed through the long chain of photosynthesis, food, metabolism, and motion. You're one of the planet's engines, small, warm, and luminous in your own way. There's something humbling in realizing that your heartbeat, and the swirling of storms obey the same principle. Both exist because of difference. Both rely on imbalance. It's a fragile equilibrium, though. Too much energy trapped near the surface, and the balance falters. The planet warms. Too little, and it freezes. For most of Earth's history, that balance has wavered but endured, allowing life to adapt and thrive. When the first plants appeared, they tilted the system even further toward complexity. They trapped sunlight more efficiently, reshaping the atmosphere and cooling the world. Every living thing since then has been part of this fine adjustment, a global web that keeps entropy flowing in just the right measure to sustain change without collapse. The brilliance of this natural engine is not its power, but its patience. It doesn't rush. It never overreaches. It turns sunlight into seasons, heat into growth, imbalance into motion, all through a rhythm so subtle we forget it's there. And when you think of it that way, you start to see that life is not a miracle standing apart from physics. It's physics expressed as grace. The Earth doesn't fight entropy, it dances with it. Every transformation, from sunlight to shadow, is another step in that dance. Entropy increases, yes, but in the process the universe gets to know itself through patterns, waves, storms, forests, minds. The next time you feel the warmth of sunlight on your skin, remember that it's part of a vast conversation. The sun speaks in bright, focused light. The earth answers in a long, soft sigh of heat. And you, and everything you love, live in the pause between those two breaths. From here, our story will drift further backward, toward the beginning, to a time before engines, before stars, before even light itself had space to travel. Because if entropy defines the direction of time, then we must ask, what was it like at the very start when the universe had not yet chosen which way to flow? To understand why time flows at all, we have to step back, far beyond the blue earth, past the stars and galaxies, back to a moment when there was no light, no sound, and no direction for anything to move. It's hard to picture the beginning of the universe. Words like before and after lose their meaning, because time itself hadn't yet begun to tick in the way we know it. And yet, something remarkable happened there. Something that would set the arrow of time forever pointing forward. Physicists call it the low entropy beginning, the smooth, ordered dawn of everything. But what does that really mean? Imagine an empty field of snow, untouched, silent, perfect. There's no mark, no disturbance, no footprints. It's beautiful in its simplicity. But the moment a single step is taken, that perfection begins to change. The snow compresses underfoot, air stirs, sound carries, and suddenly there's a before and after. Entropy has begun. The early universe was like that pristine field, not chaotic, but almost too smooth. When we look at the cosmic microwave background, the faint afterglow of the Big Bang, we see a pattern of temperature so uniform that the differences between one point and another are less than 1 part in 100,000. That smoothness is what made it low in entropy. To most of us, the word disorder sounds messy, but in cosmology, disorder means variety, complexity, unevenness. A uniform, featureless universe is paradoxically highly ordered, because there are so few ways to arrange it. There's only one way for everything to be perfectly even, but countless ways for it to be uneven. In the very beginning, the universe chose the rarest of all states, an astonishingly balanced, symmetrical beginning. That balance was fragile. It contained all the energy and matter that would one day become galaxies, stars, planets, and us. But for that first instant, it was still, almost frozen, like a deep breath waiting to be released. Then, gravity, that gentle, relentless sculptor, began its work. Gravity is strange among the forces of nature. Unlike heat, which spreads things out, gravity gathers. It pulls matter together, making stars and planets out of the uniform gas. And paradoxically, That act of gathering, of forming clumps and structures, increases entropy. If that sounds confusing, think of it this way. When matter is spread perfectly evenly, there's only one simple way it can exist. But when gravity lets it clump into many forms, stars, planets, dust, voids, the universe gains complexity. It has more ways to arrange itself, and therefore more entropy. In other words, structure is not the opposite of entropy. It's one of the ways entropy expresses itself. The smooth beginning of the universe was, therefore, a state of improbably low entropy, a state so special that physicists still don't know why it happened. It's sometimes called the past hypothesis, the idea that the universe started out in a condition of extreme order, and everything that's happened since has been the process of that order relaxing into variety. You could say that time itself is just the name we give to this relaxation, to the unfolding of that first perfect stillness. If the universe had begun in a high entropy state, full of disorder from the start, nothing would ever have happened. There would have been no direction for time to flow, no imbalance to set things in motion. But because the beginning was so ordered, there was something for entropy to increase from. That from is what we experience as history. Every second since that beginning has been a step in the same direction. From simple to complex, from smooth to clumpy, from hot to cool, from potential to memory. Time, in that sense, is not an independent thing ticking away like a metronome. It's the measure of the universe's gradual letting go. Sometimes physicists describe this in equations that connect entropy to probability, the idea that as the universe evolves, it naturally explores the states that are most likely, and those states tend to be more spread out, more entropic. But we can describe it more softly. The universe moves toward what is easier, what is gentler, what requires less tension. It's the same principle that makes a ball roll downhill or a cup of tea cool on the table. Everything relaxes, not because it's forced to, but because that's where possibility lies. The direction of time, the reason you remember yesterday but not tomorrow, comes from this single profound imbalance. The fact that the universe began smooth and became rough. The arrow of time is gravity's signature, written across the sky. When stars began to form, they gathered gas into immense shining furnaces. In doing so, they increased the universe's entropy even more, releasing radiation, heat, and light, all forms of energy spreading outward. And yet within that spreading came life. The same imbalance that drives time also drives creation. You might say that time began the first moment the universe lost its perfect stillness. Every photon emitted, every atom formed, every collision and cooling and gathering, all of it is the unfolding of that initial imperfection, and what an extraordinary imperfection it was. It's strange to think that everything, the light from distant galaxies, the warmth of the sun, the breath you take right now, traces back to that one improbable condition. A beginning where the universe was both full of energy and nearly featureless. If you could whisper into that first moment, you might say, "Thank you for being slightly uneven." Because without that imbalance, nothing would have happened. The earlier stars were born from tiny fluctuations in that smoothness, faint ripples of density that grew under gravity's pull. Over billions of years, those ripples became galaxies, and galaxies became the scaffolding for everything that followed. Suns, planets, oceans, forests, and the quiet thought forming in your mind right now. Entropy began small, but it never stopped growing. It's what allows matter to change, to evolve, to become self-aware for a brief moment before returning to the flow. The low entropy beginning was not a mistake nor a miracle, but a kind of cosmic generosity. It gave the universe room to expand, to try things, to learn how to shine. And so, the next time you look at the night sky and feel the passage of time, the pull of days and years slipping by, remember that time itself is not a current pushing you forward. It's the slow spreading of possibility a ripple that began in a field of perfect stillness and has never stopped widening. From here, our journey will carry us through the next great act of this unfolding, the birth of stars, galaxies, and planets. We'll watch as gravity and entropy, two quiet partners, weave the complexity that fills the cosmos, and as each sunrise becomes a small echo of the universe's very first awakening. If you look up at the night sky, really look until the stars stop being points and start feeling like whispers, you're seeing entropy at work, wearing its most dazzling disguise. Every shining star is both a cradle and a grave. It's where order unravels and beauty is born in the same breath. And though we often think of entropy as a quiet, invisible process, the soft spreading of heat or the fading of light, it is in the hearts of stars that it becomes radiant, visible, alive. The story of every star begins with gravity. After the smooth dawn of the universe, matter began to gather. The first clouds of gas, mostly hydrogen with a little helium, drifted in the dark, pulled together by their own faint attraction. Slowly, over millions of years, they condensed. The gas grew denser, the pressure rose, and as it did, the atoms began to move faster, colliding more fiercely. There's a moment in that long collapse when the balance tips, when the pull of gravity and the push of heat finally meet in a delicate truce. The core of the cloud grows hot enough for fusion to ignite. Hydrogen atoms fuse into helium, and in that instant a star is born. From one perspective, this process seems like a rebellion against entropy, gas gathering into form, light arising from darkness. But in truth, it's entropy's grandest flourish. The fusion inside a star releases energy, spreading it across space in every direction. That outward flow of radiation is the very definition of entropy increasing. A star's order, its shape and symmetry are simply the structures that make that spreading possible. You can think of a star as the universe's most elegant engine, a self-sustaining system that converts concentrated mass into radiant disorder. For every second that the sun shines, it fuses around 600 million tons of hydrogen into helium, releasing photons that will travel outward for thousands of years before escaping into space. It's hard to grasp what that means in human terms. Each of those photons began as a fragment of perfect order, mass bound tightly by gravity. In transforming that mass into light, the star allows that order to relax, to scatter, to breathe. The result is a balance between creation and decay so perfect that it can last for billions of years. Our own sun has been performing this balancing act for 4.5 billion years, and it will continue for about 5 billion more. All the warmth and life on Earth, every forest, every ocean, every living thing, is a side effect of the sun's slow, radiant surrender to entropy. And yet, that surrender builds complexity. Because as the universe spreads and cools, entropy doesn't erase structure, it creates it. The energy released from fusion fuels chemistry, drives motion, and builds patterns that wouldn't exist without imbalance. Stars forge the elements, scattering them through space when they die. The calcium in your bones, the iron in your blood, the gold in a ring. All of it was born in the entropy of dying stars. There's a paradox in this. The same process that leads to cosmic disorder also makes every atom of beauty possible. Entropy and structure are not enemies. They are partners in an infinite dance, one spreading energy, the other arranging it into temporary harmonies. Stars are the choreography. When a massive star dies, it releases a final, luminous breath, a supernova. For a brief moment, it outshines entire galaxies, releasing more energy than the sun will emit in its entire lifetime. The explosion tears the star apart, scattering heavy elements into space. That debris drifts, cools, and eventually gathers again into new clouds, new stars, new planets. Each generation becomes more complex, more enriched with the ingredients for life. If you could trace it all backward, you'd find that the atoms in your body, the carbon in your cells, the oxygen you breathe, were once part of a star that burned and died long before the sun existed. You are quite literally a fragment of ancient entropy, rearranged into consciousness for a brief moment in cosmic time. That realization isn't bleak, it's breathtaking. It means that even in its constant slide toward equilibrium, the universe creates islands of order where it can observe itself, think about itself, and feel awe at its own unfolding. In physics, scientists sometimes describe entropy mathematically as a measure of microstates, the number of ways a system can arrange itself without changing its outward appearance. But said softly, entropy is simply possibility. The more possible ways something can be, the higher its entropy. Stars increase the universe's entropy not by destroying structure, but by unlocking new possibilities. Before stars, there was only hydrogen and helium, a simple, quiet cosmos. After stars, there were oceans of elements, planets, and the raw materials for chemistry and thought. In that sense, every sunrise is entropy in bloom, the daily reminder that the same process that will one day cool the cosmos also gave rise to colour, warmth, and life. Entropy's rise is not a fall from grace, it's a passage into complexity. The universe doesn't tumble downward into emptiness, it expands outward into variety. And even when the stars fade, the story won't be over. Their remnants, white dwarfs, neutron stars, black holes, will continue to shape the universe's entropy, storing its memory in gravity and radiation. Each collapse, each emission of light, each whisper of heat into the dark background adds one more note to the music of time. From Noether's perfect symmetries to entropy's graceful asymmetry, everything we know emerges from this interplay. Balance and imbalance, order and release. Without symmetry, there would be no conservation, no laws of physics. Without asymmetry, there would be no motion, no time, no life. The universe's beauty comes not from perfection, but from its willingness to bend, to change, to create through imperfection. When you look at the stars tonight, remember that their glow is not the triumph of light over darkness, but the signature of balance finding its rhythm, the slow unfolding of entropy into elegance. Each photon that reaches your eyes has travelled across billions of years, carrying the story of that balance, of order giving way to freedom, of gravity sculpting heat into brilliance. And someday, when even the stars themselves are gone, that story will continue, written in the faint radiation left behind, in the quiet memory of space itself. But for now, we live in the golden age of complexity, a moment when the universe still burns, still creates, still dreams. And as we drift further into that dream, the path ahead will lead us once more towards stillness, to the far horizon where entropy reaches its final gentle maximum, and time itself may come to rest. If the stars are the bright exhalations of the universe, then black holes are its quiet inhales, the pauses between cosmic breaths. They are the still points where light itself forgets how to leave, where gravity grows so deep that even time begins to bend towards silence. But in that darkness, something extraordinary happens. Black holes, for all their mystery, are not the monsters we once imagined. They are the universe's memory keepers, vaults that hold almost all its entropy, storing the record of everything that has ever fallen into them. The story of a black hole begins at the end of a star. When a massive star exhausts its fuel, its shining balance collapses. The outward push of fusion fades, and gravity, that patient sculptor, finally wins. The star folds in on itself. Its core compresses, tighter and tighter, until the atoms themselves surrender, their structure breaking down into something beyond our comprehension. The collapse continues until the mass is so dense that escape becomes impossible. Not even light can climb out. We call that boundary the event horizon, a place where space and time trade roles. Inside, movement becomes meaninglessly inward. Outside, the universe keeps expanding as if nothing happened. From far away, the black hole is invisible, except for the way it distorts everything around it. It bends light, slows time, and draws the orbits of stars into graceful, perilous curves. But while the center is hidden, the surface, that horizon, holds the real secret. In the 1970s, physicists began to notice something astonishing. They realized that a black hole's entropy, its measure of disorder, doesn't depend on its volume, but on the area of its surface. The bigger its horizon, the greater its entropy. It's as though the universe writes the story of everything that falls into a black hole, not in the depths, but on the skin of its shadow. The information, the details of every particle, every photon, is stored on that boundary, woven into the fabric of space itself. If you tried to translate the mathematics of it into words, you could say, the more stretched the surface, the more the black hole knows. The measure of its entropy grows with its area, like pages in a book that expand as the story grows longer. This discovery changed the way we think about the universe. It suggested that reality might not be a vast three-dimensional stage after all, but something like a grand projection, where everything we see, everything that happens, could be encoded on a cosmic surface, a holographic boundary too vast for us to perceive. Black holes became not just endings, but mirrors. They also defied one of the most sacred assumptions in physics, that nothing can escape them. In the mid-1970s, Stephen Hawking discovered that black holes are not completely silent. According to the strange rules of quantum mechanics, even the vacuum of space is alive with flickering pairs of particles, one matter, one antimatter, appearing and disappearing faster than a blink. At the edge of a black hole, one of those particles can fall in while the other escapes. The escaping particle becomes real, carrying away a whisper of energy. Over immense timescales, the black hole slowly shrinks, losing mass as it radiates. This faint glow, Hawking radiation, means that even darkness glows if you wait long enough. It's such a delicate process that no one has yet seen it directly. A black hole the mass of the sun would take longer than the current age of the universe to fade completely, but the mathematics tells a quiet, consistent story. Even the deepest night hums with a temperature. Even absence carries warmth. The surface of a black hole, the same surface that holds its entropy, also defines its temperature. The larger the black hole, the colder it is. A small one would glow faintly with heat, while a supermassive black hole, the kind that sits in the heart of galaxies, would be almost perfectly cold, its warmth so faint that it makes the surrounding stars look like fireflies. The universe seems to love balance. The greater the shadow, the gentler its breath. Black holes in this way are paradoxes of peace. They are the places where entropy reaches its most concentrated form, and yet they are also the anchors of structure. Without them, galaxies would drift apart. Their gravity shapes the spiral arms of stars, their slow hunger setting the tempo of cosmic growth. Even their violence, their ability to tear and consume, is part of the universe's way of conserving meaning. Nothing that falls into a black hole is truly lost. Its energy, its information, its essence is stored, encoded, waiting. In the vast accountancy of the cosmos, not even darkness forgets. Some physicists now believe that black holes are the universe's ultimate hard drives, their surfaces covered in quantum ripples that preserve the story of everything they've touched. Others see them as portals to deeper understanding, clues that the laws of physics themselves are incomplete. But beyond the equations, beyond the debates, there's a gentler way to think of them, as the universe's memory of itself. Each black hole is a note of stillness in the grand symphony of entropy, a place where energy and order, gravity and light come together and pause. If you could stand near one, though you never could, you wouldn't see horror, you'd see serenity. The stars around it would appear to freeze in place, their light stretched into slow, deep red waves, fading into forever. You'd be standing at the edge of time's patience. And yet, even black holes are temporary. Over incomprehensible ages, their faint radiation will carry away their mass, one whisper at a time. Eventually, they will evaporate completely, leaving behind only the soft echo of their warmth. When that happens, the universe will enter its quietest era, the age of silence. The stars will be gone, the galaxies dim, and only the fading heat of the black holes will remain. But not yet. For now, they still anchor the heavens, like punctuation marks in the story of creation, commas in the universe's long sentence. As we drift further into this story, we'll follow them toward that silence, to the far future when even their whispers fade and the universe itself begins to forget how to change. Imagine a night so vast and silent that even the concept of darkness begins to dissolve. No stars, no galaxies, no flicker of light. Only a quiet field of nothing, stretching forever. This is not a void of despair, but of completion. The universe at rest after a lifetime of creation. It's called the heat death of the universe, though the name feels too harsh for something so peaceful. It's not really death, because nothing truly ends. It's simply the moment when all contrasts fade, when every hot and cold, bright and dark, near and far finally even out. The great temperature differences that once powered stars, storms and life will have been erased by time itself. In that distant future, all the stars will have burned their fuel. The last red dwarfs will wink out, leaving behind cold remnants, white dwarfs, neutron stars, black holes. Even they will fade, radiating their remaining warmth into the infinite dark until every corner of space shares the same temperature. You can think of the universe as a grand orchestra. For billions of years, it's been playing a magnificent symphony, galaxies colliding like cymbals, supernovae bursting like trumpets, black holes humming their deep bass tones. But one day, the music will slow, the instruments will soften, and finally the last note will fade into a single endless hum. When nothing changes, does time still move? That's the question that lingers at the end of physics, because time, as we know it, is defined by difference, by the flow from one state to another. It's the measure of change, and when everything reaches perfect balance, when no part of the universe can give or take energy from another, there's no longer a reason for time to have direction. It's as if the cosmic clock still exists, but its hands have stopped ticking. At first, that idea might feel sad. The notion that all motion will end, that even thought and warmth will dissolve into the same still equilibrium. But look closer, and there's something strangely comforting in it. The universe has been rushing forward for almost 14 billion years, expanding, cooling, creating stars, building life. It's been a long journey from that first flash of light to the quiet glow of our modern sky. Heat death is simply the final exhale, the moment when the universe lays down its instruments and rests. And even then it won't be empty. Space will still shimmer with the faintest warmth, a whisper of the energy that once lit 1,000 billion suns. That glow will be stretched thin, its wavelength, longer than any visible colour, a ghostly background filling all of existence. Every photon will wander endlessly, carrying the memory of what once was. It's easy to imagine this future as frozen, but temperature itself will still exist. It will just be the same everywhere. There will be no gradients left, no edges, no flow. You can picture it as a vast ocean that has finally gone still, every wave flattened, every ripple smoothed. Entropy, the universe's quiet architect, will have completed its work. Every imbalance will have been shared away. The strange thing is, this state of maximum entropy isn't chaos. It's the most even order possible. It's a balance so complete that it erases the need for further motion. The story of physics ends not in fire but in peace. Perhaps that's why so many scientists, when they speak of the end, use words like calm, stillness, or elegance. It's not an apocalypse, it's a resolution. And somewhere, maybe, there will still be remnants. Ancient black holes evaporating one by one, their final whispers of radiation slipping softly into the sea of equilibrium. Each tiny burst will be the last spark of the old universe letting go. If you were somehow there, not as a body but as awareness, what would you see? There would be no light, no horizon, no here or there. Space itself would have expanded beyond all recognition. The galaxies that once filled the sky would be gone, their ashes dispersed. Even the idea of a sky would be meaningless. But in that unimaginable stillness, you could say that the universe has found what every living thing searches for: rest. For us, time feels urgent. We measure it in seconds, years, memories. We chase it, lose it, wish for more of it. But the universe has a patience beyond anything we can grasp. It doesn't rush toward its end. It glides there, one slow breath at a time. If you listen to the hum of background radiation, the faint microwave whisper that fills the cosmos even now, you're hearing the echo of the universe's earliest light, stretched thinner with every passing eon. Someday, even that whisper will fade below detectability, but it will never truly vanish. The information, the memory, will remain woven into space itself, hidden but not erased. And so, maybe time doesn't end. Maybe it just becomes something too still for us to recognize. Physicists sometimes imagine this far future in terms of unimaginable scales, numbers so large they can't be spoken. Trillions upon trillions of years will pass between the last sparks of light. But from the universe's perspective, that timescale is irrelevant. Time is a property of change, and when change slows, time simply loses its meaning. It's as if the universe has drifted into a deep, dreamless sleep, not gone, but resting between breaths. Some theories even whisper of renewal, that beyond this stillness, quantum fluctuations might one day seed anew. Beginning, another burst of low entropy, another dawn. Whether that's true or not, the idea carries a quiet comfort, that nothing is ever truly lost, only transformed. From our vantage point, a tiny spark of consciousness, living in one bright instant between the universe's beginning and its rest, it's impossible not to feel humbled. We are part of that same unfolding, that same cosmic rhythm. Our thoughts, our lives, our stories, all are tiny ripples in the long exhalation of entropy. And yet, how beautiful those ripples are. When the universe finally reaches its balance, when time stops counting, the echoes of everything that ever was will still exist, not as light, not as sound, but as structure, faint and eternal. The memory of every motion, every star, every life will be written into the stillness itself. It won't be an ending, but a kind of homecoming, the cosmos returning to the same equilibrium it began with, now filled with everything it has ever learned. From here, the story opens again, not forward, not backward, but inward, toward the realization that all beauty, all thought, all complexity arises not at the extremes of order or chaos, but somewhere in the middle, in that delicate tension between stillness and motion. If the universe will one day fall silent, and if it began in perfect stillness, then the miracle of existence must lie somewhere between those two quiets, in the middle, between order and chaos. That's where we live. It's easy to think of life as something apart from physics, a bright spark rising out of the void. But when you look closely, you see that it follows the same deep rhythm that governs everything. The slow balancing of differences, the steady climb of entropy. Life is what happens when the universe finds itself in just the right kind of imbalance. Not too still, not too wild, just enough tension for patterns to form. You can see it in something as simple as a cup of tea. Pour in a swirl of milk, and you'll notice that at first there's order. the milk distinct from the tea, curling in smooth white ribbons. Then comes chaos, the turbulence, the whirl, the blending, and finally the mixture settles into uniform calm. Life exists in that middle moment, while the swirls are still forming before everything blends away. Too much order, and nothing moves. Too much chaos, and nothing lasts. Our world sits precisely in that narrow window where entropy is rising but not yet done. The sun is still burning. The earth is still cooling. Oceans still move, storms still breathe, and every living thing rides the gradient between light and dark, hot and cold, possible and spent. Physicists sometimes call this a non-equilibrium system, but we might just call it life's sweet spot. In such systems, energy flows through without settling. Order appears not because entropy is resisted, but because it's guided. A leaf, a flame, a human mind, all are temporary shapes carved by energy on its way to dispersing. It's as if the universe discovered long ago that the best way to relax is not all at once, but in patterns, spirals, waves, music, thought. You can picture this as a dance between two partners. On one side is order, still and precise. On the other, chaos, wild and free. Life is their shared movement, their steps weaving together into something both unpredictable and harmonious. Every hurricane, every heartbeat, every flicker of thought exists in that thin band of balance. We live, think, and love because the universe has not yet finished equalizing itself, because there's still difference left to share. The philosopher and physicist Ilya Prigogine once said that far from equilibrium systems, like living things, don't resist entropy, they use it. The energy flowing through them allows new structures to emerge. The whirlpool forms because water must move. The flame dances because heat must escape. You do not burn energy despite entropy. You burn because of it. So life, in its deepest sense, is entropy in motion. The universe practicing complexity on its way towards simplicity. That may sound abstract, but you can feel it in your own body. The warmth of your skin is sunlight transformed, part of the Earth's continuous exchange with the sky. Every breath you take, every thought that flickers through your brain is powered by gradients, tiny imbalances between chemical and electrical states that allow movement and awareness. The fact that you are alive at all means you're sitting at the perfect midpoint between the stillness of the void and the chaos of total disorder. Our planet too lives in that balance. It orbits at just the right distance from the sun, not too hot, not too cold. Its atmosphere traps just enough warmth to sustain water and life. The flow of energy through its systems, from sunlight to ocean to air, keeps everything dynamic without tipping into destruction. This middle ground is fragile but fertile. It's where evolution happens, where complexity builds, where thought arises. The universe creates its greatest wonders not by avoiding entropy, but by lingering in its midst, letting difference linger long enough to weave beauty out of decay. In this way, the cosmos mirrors our own inner worlds. Our minds too need a balance between order and freedom. Too much structure and creativity dies. Too much randomness and meaning dissolves. Understanding, art, love, they all grow in the same gentle zone of tension where certainty meets curiosity. You could say that the universe is a vast improvisation, and we are part of its melody. Each of us a fleeting harmony between structure and surrender. Even galaxies obey this rhythm. Their graceful spirals are born from the tension between gravity pulling inward and rotation pushing outward. Mountains rise because tectonic plates meet in resistance. Rivers carve valleys because they are always falling. Everything that moves or breathes owes its existence to difference. If the early universe had been perfectly uniform, nothing could have formed. If it had been too chaotic, nothing stable could have lasted. Life, matter, thought, they all depend on the narrow margin between extremes. There's a quiet wisdom in that. When you think about it, the same principle guides human experience. Our lives too unfold between opposites: hope and despair, comfort and challenge, love and loss. Meaning arises not from escaping those contrasts, but from living within them. We need tension to grow, friction to learn, contrast to see beauty. Entropy teaches us this lesson gently. It reminds us that change is not an enemy. It's the essence of being. So perhaps the goal of understanding isn't control. It's not to stop the flow, but to see it clearly, to appreciate its grace. Science, at its best, is an act of wonder, a way of listening to the music that underlies everything. And maybe that's the purpose of awareness itself, to witness the universe as it balances between symmetry and drift, to find peace in knowing that both are necessary. In the end, life is not a fight against entropy, it's the celebration of it. We are the temporary shapes entropy takes as it learns how to let go beautifully. When the stars fade and the last warmth slips into the cosmic night, that balance will finally resolve into silence. But until then, while energy still flows and time still stretches, we are here, awake in the middle, watching the universe play its favourite note, the one between order and chaos. And as that note fades into stillness, one last thought remains, that maybe understanding all this, quietly and without fear, is the most human thing we can do. Imagine again that small rock, drifting through space, the one we met at the very beginning of this journey. You might remember it. A simple stone, moving quietly between stars, slowing ever so slightly as it travels through the cosmic sea. Back then, it seemed like a paradox. If energy is conserved, we asked, why does anything ever slow down? Where does the motion go? Now, after wandering through the worlds of symmetry, entropy, and time, we can see the answer softly. The rock never breaks the law of physics, it simply becomes part of a larger story. Its motion doesn't vanish, it spreads. The energy that once lived in its path dissolves gently into heat, into radiation, into the expanding air of the universe. Nothing is lost, but everything changes form. That's how the universe plays its music. Noether's symmetry gave us the rules, the steady rhythm that keeps the melody consistent. Entropy gave us the motion, the slow, one-way flow that carries the song forward. And life, fragile, temporary, beautiful, added the harmony, giving that motion meaning. Energy fades, time flows, entropy grows, and yet through all of it, something astonishing remains: awareness. You are the universe, listening to its own echo. Every thought you have, every breath, every small flicker of wonder is the cosmos experiencing itself for a brief, shimmering instant. When Emmy Noether proved that conservation laws arise from symmetry, she showed us that beauty is not decoration, it's the foundation of reality. The order we see in nature, the patterns of orbit and light, the balance between forces, all of them exist because the universe loves consistency. For every motion, there is a reason. For every transformation, a quiet rule. But the universe also loves imperfection. Entropy, that slow drift from order to disorder, is what gives the song its rhythm. Without it, everything would remain perfectly symmetrical, perfectly still, and therefore perfectly silent. If symmetry is the score, entropy is the performance. Each act of imbalance, each photon leaving a star, each atom vibrating in warmth, is another note played in the great composition of existence. Over time, the song grows softer, the instruments more distant, but the melody continues, stretching across all space. And here, on this small blue world, a few conscious beings have learned to listen. When you look at the night sky, you're not just seeing the past, you're hearing the universe's music at different points in its score. The light from nearby stars hums a few beats behind the present, while the glow of distant galaxies plays notes that were written billions of years ago. Even the faint cosmic background radiation, the leftover hum from the Big Bang, is part of the same eternal song now slowed to a whisper. Somewhere in that vast composition, our tiny melody plays, fleeting, fragile, human. It's humbling to realise how brief our moment is. The universe has already seen the birth and death of countless stars, and it will continue long after our sun grows dim. But brevity doesn't mean insignificance. The smallest sound can still change the texture of a song. The universe's beauty is not in its size, but in its coherence, in the way every motion, from the spin of galaxies to the firing of neurons, participates in the same flow. Perhaps that's what consciousness is, the universe pausing for a moment to hear its own harmony. Think of how improbable it is that you exist. A collection of atoms arranged just so, capable of reflecting on time itself. Those atoms were forged in stars that lived and died billions of years before the Earth was born. The warmth in your hands once blazed in the heart of a sun. The oxygen you breathe was woven by ancient leaves. The calcium in your bones was built in the death throes of a supernova. You are, in every sense, a symphony made of starlight and memory. And though your part in the song will one day fade, the notes you play, your thoughts, your kindness, your curiosity, ripple outward, absorbed into the wider pattern. Nothing is ever truly gone. It only becomes quieter. Even in physics, this idea holds. Information, as far as we can tell, cannot be destroyed. It transforms, hides, disperses, but it endures, just as the echo of a sound lingers in the air after the music stops. So perhaps, in some unfathomable way, the universe never really ends. Its melody stretches on slower and softer until it becomes a hum below perception, a single, infinite chord sustained by everything that ever was. You might imagine it as a lullaby sung across eternity, one that began with the Big Bang's first brilliant note, swelled through the lives of stars, whispered through the birth of life, and now hums quietly in your chest as you breathe. That hum is what connects everything. The symmetries that preserve, the entropy that transforms, the awareness that listens. And here we are, together, floating inside that music. The rock still drifts, the stars still fade, the universe still expands, and yet through all of it the melody continues. Patient, graceful, unresolved. It's comforting, isn't it? To know that you don't have to fight time. You're part of it. You're made of its flow. Every heartbeat, every thought, every sigh is a translation of cosmic rhythm into human form. Noether showed us that structure is eternal. Entropy shows us that change is inevitable. Life shows us that awareness gives those truths meaning. And so, when you think of energy fading, don't picture loss. Picture transformation. Picture light spreading across space until it becomes silence. Not because it vanished, but because it became everything. That's what it means when we say the universe is still playing its song. The tempo slows, the notes drift apart, but the music never truly ends. And maybe that's the quiet secret hidden inside all of physics, that the universe doesn't seek permanence but participation. It doesn't want to last forever. It wants to be experienced. So tonight, as you drift towards sleep, you can let go of trying to hold time still. The music will continue whether you listen or not, softly, patiently, endlessly. Energy fades, time flows, entropy grows, and yet here you are, listening, thinking, alive. The universe's way of wondering where its own music goes,